Today I want to talk about devices. We'll begin a series, maybe 3 lectures or so, where we will discuss devices that are based on semiconductor materials. And the first thing that I want to take up is a continuation in part of what we were doing the other day, dealing with Schottky junctions. We just studied the Schottky junction, and we will see a couple of simple applications in the area of photovoltaics. I'm not going to go into great detail with any of these devices, except maybe the PN junction, which is a very fundamental one that we will look at to some extent. But other than that, we'll go briefly over the different kinds of devices. Now, in the area of photovoltaics, there's great importance to the solar cell kind of applications because of the great energy crisis that we are facing. We see a lot of problems in generating fuel. Partly that's what this whole war is about right now that is taking place. And in the coming years, it's going to be even worse, that we will have a lot more of problems related to acquisition and use of fuel. So solar cell technology is something that's going to be very important in absorbing the energy from the sun and converting it to electricity. So we can make use of a Schottky junction to do this. And basically how we would go about it is to evaporate a thin film of some metal, for example, in this case gold, say onto silicon, some kind of N-type semiconductor, commonly some kind of silicon maybe, or amorphous silicon. Variations are there which we are not going to go into. And when we say thin film, we are talking about something like 10 nanometers. This is thin enough to allow the passage of light through it, and yet it will serve as a Schottky contact to gold, to the N-type semiconductor. And what we have here is that light will now fall on this device, and provided that the photons in the light have an energy greater than the band gap, Eg, of the semiconductor, let's call that the depletion layer. As we saw earlier, there's a depletion layer with width W. And when light falls on this, in this depletion layer, a lot of electron-hole pairs are generated as we get a transition from the valence band to the conduction band. Now, in addition, what happens to that is that because of the presence of the built-in electric field, we have a field that is directed in this direction because of the presence of the positively charged cores that are left here after equilibrium was established. That's why we have the depletion layer here, where there's no free carriers. And because of the presence of this field, the electrons and holes that are generated as part of this photo generation process will drift under the application of an electric field, and the electrons will move in one direction and the holes in the other direction. So if we were to represent this in terms of the band picture that we drew earlier, we have something like this. And that's, say, my depletion layer width. And what we are saying here is that we have electrons and holes, pairs that are being excited out of here. Electrons go into the conduction band. And then under the presence of this electric field that is existing, a built-in field, what's going to happen to the electrons? The electrons are going to drift in this direction, and the holes are going to drift in this direction. This is due to the electric field that is built in there. So we have the metal here, and we have the N-type semiconductor here. Now, the area that is beyond the depletion level is a neutral part of the N-type semiconductor. This is the part that has got a space charge, what we call space charge layer or the depletion layer. So now we have electrons that are generated drifting in this direction more into the semiconductor, and we have holes that are generated drifting towards the metal. And as these holes come here, they are going to recombine with electrons that are in excess and effectively create a more positive charge. So what we are doing is making this side more positive and this side more negative. Remember, this is an open circuit. We have no external load. and so the charge builds up, and effectively we have an open circuit voltage. That is, as long as the light is shining, electrons will be generated, electron hole pairs generated, and electrons will drift in one direction under the built-in field, holes will drift in the other direction, and we will build up a potential across the semiconductor, with this side becoming more and more negative and this side becoming more and more positive. Now what happens when we connect this to some kind of an external load through wires is that the electrons that are accumulating here can now flow through those wires through an external load and do work for us, and then they combine with the holes that are here. And this process will continue as long as there is sufficient light generating electron hole pairs. This is essentially the basis of the solar cell technology that we can look at. We have solar cells that are based on a Schottky junction like this, and the current that will flow is due to the absorption of energy of sufficient energy to excite from the valence band to the conduction band, and current will flow in the external circuit. I can draw that again this way, that we have, as before, the depletion layer, and electrons are drifting in this direction. This is connected now to an external load, and electrons are going to flow in this direction, meaning current is going to flow in this direction when we have illumination H nu greater than Eg. So this is how we get work done by converting the solar energy, or any incident light it may be. Particularly this is the basis of the solar cell, and we can use that then to get some useful electrical energy. Now the thing is that even if we don't have illumination that is strong enough to cause excitation from here to here, namely that even if H nu is less than Hg, even if H nu is less than Eg, okay, I didn't draw that in here, H nu is the incident light. Even if that is less than Eg, it is still possible to get some work out of this, though not the same as when you have incident. The way that would work is that basically all I need is there's lots of electrons here in the metal, in the Fermi level here, and we can excite it over here. So as long as this is our phi b, if you remember, as long as there is enough energy in the light to excite electrons from the metal over the barrier into the conduction band, the same thing will apply, because again the electron will drift under the built-in field in this direction, and we will get work current in the external circuit. So it doesn't mean that only the light which has got the exact energy greater than Eg is useful. Even some amount of the light where H nu is less than Eg but sufficient to cause excitation over phi b will be useful. But we must realize that in that process we are not generating any holes. It's simply taking electrons from the conduction from the Fermi level of the metal and putting it into the conduction band, which is different from, in this case, we've got holes also being generated in the depletion layer. So remember, in a semiconductor the total current is given by the current flow due to the electrons as well as that due to the holes. So we'll see a little bit of a different behavior in both these cases. The same idea can be used for what will be a photodetector. I will use the Schottky junction to detect the presence of light, and you can use the same Schottky junction, except we operate this now under reverse bias. And you will recollect that when we did that under reverse bias, let's call that the same W. So this side is my N-type semiconductor and the metal. We have a reverse bias voltage of its negative VR. And then we know that the built-in potential has changed, if you recollect from yesterday, has changed from being EV naught, it has changed to being plus VR. And given that VR is much greater than V naught, that's fractions of a volt, few volts, we are also seeing then that the field which is related to this is much greater than the built-in field which was there in the absence of any bias. And because this field is there acting in the same direction, but it's a much stronger field that we have now, the electrons will be accelerated faster through this depletion layer. In other words, in a photodetector, I'm trying to improve its response time. How quickly can it tell me if there is light? So when light is falling on this sample here, as before it is going to be, say, a metal that is gold, and I had told earlier 10 nanometers or so, very thin to allow light to pass through that contact. Again, in this case, we have the same behavior as the generation of electron hole pairs and so on, except that in the presence of this higher field, the electrons are going to drift much faster through the depletion layer. And so we get a quicker response. I forgot to include a resistor here through which we will measure a current. I don't know if you can see that. So a current that will flow through this I photo, that is in the presence of light, the current that will flow through an external resistor can be measured very easily. And because now we have the higher field here, the system responds faster, and so we can make use of this as a photo detector. This is one scheme. There are obviously many ways of doing it. Why is it going to be faster? If you recollect, Vd was equal to mu d epsilon. Right? The drift velocity was equal to mobility times the field. Mobility is remaining unchanged, but in the presence of the built-in field, we would have had it as mu d epsilon naught. When we have the applied bias, we have mu d epsilon, and epsilon is much greater than epsilon naught. So obviously, we are increasing the drift velocity of the electrons through the depletion layer, and thereby increasing the responsivity or sensitivity of this detector. We can also make use of ohmic contacts for some useful device. One example is the thermoelectric devices, and they are very interesting and elegant. Fundamentally, the idea here is that when current flows across a junction of two dissimilar metals, you've got a DC flowing across, there is also going to be heat transfer. So depending on the direction in which current is flowing, heat may be absorbed or released. But it is in small quantities. So you can't use this, say, for example, in your home refrigerator. That would be a pretty bulky application. But for cooling down small volumes, this is a great idea. You have two, in this case, we will see the case for a metal semiconductor junction. When current flows in one direction, it absorbs heat. When it flows in the other direction, it liberates heat. And according to that, then we can use it either to heat or to cool. So the limitations here are that it's only for small volumes. And fundamentally, you can't heat or cool indefinitely. It's going to be plus minus some degrees around room temperature where it is sitting in equilibrium. So I don't know exactly what values are possible these days, but I'd easily say plus minus 30 degrees, if I'm not mistaken, around room temperature. It can give off enough heat to heat up that to say about 60 degrees, 50 degrees, or if you want to cool it down to some minus 10 or so, it can do that. So in a limited range, maybe it's not so high, I don't remember the exact value, but over a limited range, we can either heat or cool. And as I said, the basic idea is the liberation of heat or the absorption of heat. I'll use these symbols, just heat liberated and heat absorbed. When current flows through dissimilar materials. Okay, we'll look at that very briefly. Let's consider the case where you have an N-type semiconductor with an ohmic contact on it, so current can flow unimpeded in both directions. That's important. And we saw last time that in the case of an ohmic contact, our band picture is going to look something like this. Right? And what we are going to do is to have current flow in this direction through this device. Ohmic contact of some metal onto a semiconductor, and we're going to have current flow in this direction, which means electrons are going to flow from here in the opposite direction. So we've got electron transport we've biased it in such a way that now current is flowing in this direction, so electrons are flowing in this direction. Note that when the electron goes from here to say here, on an average its energy is increasing where it has gone from the Fermi level of the metal to EC. Okay? So we've got an increase of EC minus EFM. In addition, we know that in the conduction band, they have an average kinetic energy of how much? Do you remember? We are in the conduction band. Boltzmann statistics apply. You can treat it like a gas. What would be average kinetic energy of electrons in the conduction band? 3/2 kT, right? It's a gas. That's why I gave you all the clues. We are treating it just like a gas. So it's got, in addition to the change in the potential energy, it's also got a 3/2 kT. So on an average, when the electron goes from here to here, it's a very small change, but it's going to increase by this much. Okay? And so to do that, it has to take the heat from somewhere. It's got to increase its energy from somewhere. And the way it increases its energy is by absorbing heat from its surroundings. Okay? So when you have a metal to semiconductor, or I should say current flow, hang on. Current flow is from semiconductor to metal, which is the situation that is illustrated here. Current flow is from semiconductor to metal. In the case of an N-type material, we have heat is absorbed. Remember the notation I was using. Heat is absorbed. And current flow in the opposite direction then, heat is going to be released. This is true for an N-type semiconductor because of the fact that it is increasing its energy slightly, and in that process it absorbs the heat, and the opposite would be true in the reverse direction. You can do this with a P-type material, except the behavior is opposite, and I'll just summarize that here. When you have current flow from semiconductor to metal for a P-type, heat is released, and when the current flow is from metal to semiconductor, heat is absorbed. So such devices that are based on the absorption or release of heat as current is flowing across a junction are named after their inventor, or the guy who discovered this effect also, as Peltier devices, Peltier, thermoelectric or Peltier devices. Now we should remember that every time current flows through a material, it's going to produce heat. What's that called? You got a light bulb, I squared R, or Joule heating, right? Simply because of the fact that every material has got some resistance, so there's going to be Joule heating every time it flows through that. But this is different from Joule heating. It is not based on the fact that the material has some resistance. And this Peltier effect is also different in that I reverse the direction of current flow, I get the opposite effect. Joule heating, it doesn't matter whether the current is flowing this way or the opposite way. It's always going to get hot because of the presence of some finite resistance. Peltier effect, on the other hand, depending on the direction of current flow, I'm going to get a change. So it's a reversible kind of thing, unlike Joule heating. So that's some distinction we have to keep in mind. So I just, yes?
So will the current be perpetually going on, or it will go till equilibrium is maintained? That is, the field is reversed so that the electrons cannot move from metal to semiconductor?
No, it is under a bias. That's why I said we have current flow. I have to bias it externally, otherwise it won't work. So it's not creating, it's unlike in the case of the photoelectric, it was generating electricity. Here it's so it's sort of opposite. Okay, the photoelectric effect, I was taking energy from light, not from heat, but from light, and converting that to electricity. Here I'm taking electrical energy, and by passing the electrons across this junction, I'm either absorbing or releasing heat. They are not identical or exactly opposite to each other, but you see the difference between the two. Now, as we just saw that in p-type we have one behavior, in n-type we have the other behavior. So it's immediately obvious that I could combine these in the same kind of device using p and n materials to get something useful. Typically, the kind of materials that are used for this as a semiconductor are materials like bismuth telluride, bismuth selenide, antimony telluride. These are the semiconductors that are used. And for the metal, copper is a common one. Copper is also a good conductor of heat. So that's an important factor there, that because you're going to have heat transport across the junction, so you want something that can conduct heat either that is into the material or out of the material rapidly. So combinations, you make bismuth telluride, n-type, p-type, and so on, and you use p with copper and n with copper to create useful devices. Here's an example of what something may look like, one part of a whole series. Let's say this is a block from which I want to remove heat, sample to be cooled. And what I would do is to connect this through some kind of electrical insulator, but this material is a good thermal conductor. Yeah, we connect this up. Below that you'll have a copper, the metal layer, and then you have n-type semiconductor, and you have the p-type semiconductor. It's not a p-n junction, but you've got them separately there, and coupled again through copper. And then once again your electrical insulator. So this is also copper, and that's the same thing as we put here. And then you have what's called a heat sink, some way to get rid of the heat. And this is connected up then. Okay. So now we'll have current flow from here to here, n-type metal to semiconductor. It's going to take up heat. It's going to give off heat at this junction. And at this junction we've got going from semiconductor to metal in an n-type, it's going to absorb heat. In this junction also, it's p-type, from metal to semiconductor the current will flow. Okay, the current flow if we have I. And in this case we've got again absorption of heat, and at this junction liberation of heat. So as the current flows through here and comes back in the circuit, here we are liberating the heat at these two junctions here, and here we are absorbing heat. and so this is going on flowing through, and as you do that, this sample gets cooler and cooler. I said up to a point. You can't do this to make it very cold. Now you can take blocks like this, these are called single elements, and combine them all in series, a number of them, to cool down a larger plate, for example. But again, the volume that you can cool is relatively limited. So this is an application of making use of a simple ohmic contact and taking the idea of Peltier effect or Peltier cooling and applying it to produce a useful device. We can define what is called a Peltier coefficient. The heat that is liberated or absorbed, I should say the rate, hold on, rate of heat liberated or absorbed is equal to plus or minus the Peltier coefficient times the current. You can imagine that as there's more current flowing, there's more electrons doing this transfer, so more heat is released or absorbed, and this part is related to the material property itself. How much of energy will it gain in or lose in going one direction to the other? So we can have a relationship pi, I think that's a capital pi, 1 by E times, as I gave you earlier, the change in energy okay. This is how much it gains in potential. Remember, EFM is equal to EFN initially, and it will gain that much energy, and then 3 by 2 kT also in going to the in getting the average kinetic energy excess. So those complete a couple of simple devices that are practical based on the contacts that we've been talking about. I want to take us now into a little bit more details of a very fundamental device that you probably already have studied at some point, and it's called the p-n junction. We create this basically by doping both sides of the semiconductor oppositely to create on one side p and the other side is n. By diffusion you can do that, by during growth you can create it, by ion implantation. There's different ways of doing this. But fundamentally on one side you've got p-type doping, on one side you've got n-type doping. This point here where we have the interface between the two is referred to as the metallurgical junction. Okay, that physically separates the P and the N to start with when we have created it. Now things may move around afterwards, but to start with, that's where we had our junction. And in such a case, on the P side, we'll have the immobile dopants, the acceptors, Na. And on the N side, we'll have also the charged species that is not moving, Nd. Lots of free electrons on this side, and lots of free holes on this side. This is our starting point. To use a concrete example, say boron was used on the P side of silicon, so we get P-type, and on this side, let's say we doped it with arsenic to create the N-type. And before they move around, before equilibrium is established, or literally before they are in contact with each other, we have P is equal to PP naught. That's the majority carrier concentration on the P side, and correspondingly you got N is equal to NP naught, which is equal to Ni squared by PP naught, as we saw earlier. And on N side, we had N is equal to N naught, P is equal to P N naught is equal to Ni squared by N naught. This is how we started with. So effectively, there's a lot of electrons on one side, that is, this term is very high, where is it? This term here on the N side, and correspondingly this term here is very high on the P side. So when they're brought into contact, holes will start diffusing from this side to this side because there's a concentration gradient. Electrons will start diffusing from this side to this side for the same reason. So diffusional currents are set up, and diffusion of electrons will take place from N to P, and diffusion of holes will take place from P to N, simply because of the concentration gradient that we have. And when the holes that are diffusing from this side enter into the N side, they will recombine with the lots of excess electrons that are there. Similarly, when the electrons that are coming into this side recombine with the holes that are present in the P side. When electron comes this side, it is referred to as the minority carrier injection. You've taken what are minority carriers here on this, electrons are minority carriers in the P side, you're injecting them. So this process, even under bias, will be called minority carrier injection. So when they have recombined, they leave behind a region, just as in the case for Schottky, a depletion layer is created, where there are no free carriers. They injected and they recombined, there's no free carriers left there. But what is left behind is the fixed charges. You saw one part of it sort of when we were looking at the Schottky, that it left behind and created a depletion layer. The very same idea is there. Fixed charges are left behind on either side. And that's why depletion layer is also referred to as the space charge layer, or SCL. Okay? In space, they are fixed. There's charges that are fixed. And on one side, we will have fixed charges of the positive, arsenic. On the P side, we will have the boron, the negative. And so we can draw this now. After they have established, they've been diffusing onto either side, we've still got the metallurgical junction, M, and we've now created a depletion layer. On one side, there's the fixed charges of arsenic, on the other, that due to boron. Okay? There's still free carriers, obviously, on the outside the depletion layer. And now what we see is that, as before, as in the case of Schottky, we've set up an electric field in this direction, from the N side to the P side. In the Schottky case, we didn't have a P here, we had a metal there, and the same kind of built-in electric field was created. We can call the widths of each of these. On the P side, it will be called WP, and on the N side, it is called WN. That is the depletion layer width on either side. And we will say that the total depletion layer width W0 is equal to WP plus WN. Okay? We can also plot a variation of the carrier concentration after this situation is established. If we plot on the log scale, log of carrier concentration, it could be the holes or electrons, versus distance. Here we got the junction there, and the depletion layers. On this side we have P0, and on this side we've got Pn0. This is the minority carrier concentration on the N side. Similarly, something like this exists for electrons. So this is the distribution of carrier concentration after the situation has been created where we've established the space charge layer. Excuse me. Now you will notice that perhaps in the diagram I don't know if I am being consistent, but I am drawing the depletion layer width to be different on either side. Is that just my problem? I have drawn it differently, or does the depletion layer have to be equal on both sides? Is this simply that I am drawing something wrong, or we have the depletion layer on both sides equal? What would you think? Well, it turns out that we don't have the depletion layer equal on either side typically. All right, we'll see the condition when it can be equal. It is based on the idea that equal amounts of charge will be stored on either side. One side is storing positive charge and one side is storing negative charge. So we won't have equal widths because the amounts of charge on either side may be different, how much it is storing. And remember then that that is going to be dependent on how much we've doped this side and how much we've doped that side, because it is the immobile charge. Here we've got the negative charges, here we've got the positive charges. So if there's a lot more of it on this side, and it won't need that much of space to store it, an equivalent amount of charges on the other side. So it is based on doping concentration, as we will see. We define a term space charge density, which varies as a function of x. Okay? And that's basically E times doping concentration. Depending on how it is doped. So on either side, if we look, if I'm going to store charge on the P side, I will have a situation like this, which should be equal to whatever is on the N side, an equivalent volume within which it will be stored. Right? Number of charges per unit volume times the charge per carrier, and that's what we have. Now, the areas of these junctions are the same, P side and N side, assuming they're equal. It is basically then going to be E NA times the thickness. Area is the same on both sides, will be equal to E N, the thickness we can call it here, W P E N D W N. It's times an area also for volume, but the area is the same on both sides. So what we end up with is NA WP is equal to ND WN. This is a simple relation that relates WP and WN. And you can immediately see that when will WP be equal to WN? If NA is equal to ND. So if you have exactly the same doping concentration on both sides, then it will be that we will draw the space charge layer equal on both sides. But typically one or the other may not be equal, and so you'll have a distribution of the space charge layer on either side depending on the doping concentration. You'll note that if Na is larger, Wp has to be correspondingly smaller. It's inversely proportional to the doping. So let us take that Na is greater than Nd, in which case we will have, if we look at the charge storage versus X, that we will have something like this. There's a lot more of charge occupying a smaller area, so it doesn't have to be spread out so much. Here the density is less, and so it is over a larger area. So we'll get now here is my minus Wp, this is Wn. Okay, this is how they are related. Now if you remember that in the case of Schottky junction, we had the depletion layer all where? In the N-type semiconductor, right? There also is lots of electrons on the in the metal side, And that's why we ended up drawing it. Effectively, when we drew for the Schottky, we had a metal here with lots and lots of electrons, and we had an N-type here. And where we drew our depletion layer was all on this side. So as whatever was here was so much that it's inversely proportional. So we end up having the depletion layer all on the other side. Now we can try to look at the field that is built up as a result of this charge distribution that is taking place. There's going to be a built-in electric field. What will it look like? We make use of something called Gauss's law of electrostatics. You might have studied this, from which we will get that in the differential of the electric field, the gradient that you have there, is given by rho x by epsilon, where epsilon is the permittivity of the semiconductor. And which is equal to epsilon naught epsilon r, where epsilon r is the relative permittivity of the semiconductor, epsilon naught is the permittivity of free space. So we have a situation like this, and to know how does the field vary with x, we would need to integrate this. So we can determine then, integrating from minus Wp, which is the left extreme, across the diode, rho x dx. And when we do this, then we can plot for the field from Wn to 0. You're integrating it from minus Wp to x. As x changes, of course, the field is changing. So the field is a maximum at the junction. Even in the case of Schottky junction, we had seen that the field is the maximum at the interface between the metal and the semiconductor. Here also the field reaches a maximum, and the field is directed in this direction from the N to the P, and that is why it is shown on the negative scale here. This is epsilon. So this value here is the built-in field maximum value epsilon naught. So it's a non-uniform field that is increasing. This is assuming sort of uniformly graded doping there. Similarly, you can also get the built-in potential and we do that by integrating E, because we have that E is equal to minus dV by dx. So if we integrate what we got for E, then we should be able to get the built-in potential. And when we plot that as a function of x again, that's my metallurgical junction, Wn minus Wp, the potential is increasing to achieve V naught. Okay? This is, and we can get some analytical expressions. I'll come to that in a second. I'm not going into great derivations of these expressions which you can find in standard semiconductor texts, but to give you some equations that will be of use to you. But these are the kind of curves that you must have some idea about when we talk about the built-in field, the built-in potential. What does it look like in a semiconductor junction, in a p-n junction? For abrupt junctions, you've gone suddenly from the P to the N, okay, and they're uniformly doped. Remember, we could use, I just drew it without even telling you much about it, that this is like a step function. It's some value and then all of a sudden it's not there. Okay, we can approximate the distribution as a step function. It's not strictly true, but this is how we have drawn it. And if that is the case, then epsilon naught can be expressed by looking at the charge balance on both sides as before, to be equal to which is essentially what we had earlier. Nd Wn is equal to Na Wp. You've multiplied it by the charge on an electron and divided it by the permittivity of the semiconductor. So if you know this, then you can integrate this to get the V naught, which will be minus half epsilon naught W naught, because you were integrating it over the whole depletion layer width. And so we'll get an expression for V naught as equal to E Na Nd W naught squared divided by 2 epsilon Na plus Nd. Okay, I'm not going into all the derivations of it, but fundamentally it is an integration of E to arrive over the whole depletion layer with W naught to arrive at this expression. Now here I've got it in terms of Na and Nd, but I don't know what is W naught. It would be convenient if I could express the potential in terms of something that I know. And so we can go back with some rearrangements to make V is equal to Kt by E, the natural log of Na Nd by Ni squared. Okay, again I'm not going into it. So what we have here is, instead of knowing what W naught is, I've expressed the same built-in potential all in terms of things that I know. I doped it, so I know what is Na, I know what is Nd, and I know what semiconductor I'm using, so I know at that room temperature or whatever I'm considering what is Ni. So in terms of all known parameters, I get my built-in potential. And then I can use that to determine what is W naught. So if we know built-in potential here, V naught, that I can calculate from this expression, equating that to this expression, I can write an expression for W naught, which will then be W naught is equal to 2 epsilon Na plus Nd V naught divided by E Na Nd to the power half. Okay, we've basically taken the V naught expression here and equated it to this and solved it for W naught. So now I've got the depletion layer width, the total width, in terms of permittivity, doping concentration, the built-in potential that I can calculate from this equation. So I know what is W naught. And remember, W naught was equal to Wp plus Wn. I also got another expression. So this is a known term now. Here are two unknowns. I need one more expression. Remember, we also had Wp times Na is equal to Wn times Nd. Again, I've got two unknowns. Na and Nd are unknown. Na and Nd are known. So I should be able to solve for Wp and Wn independently. So starting with expressing V naught, the built-in potential in terms of these known parameters, we can calculate out W naught in terms of the same known parameters, and then we should be able to independently then determine what is Wp and Wn. One final situation, if we have that Na is much greater than Nd, is what we will refer to as a P plus N junction. I just introduced the nomenclature there. P plus refers to the fact that we've got one that much more heavily doped. Okay, when we are comparing with P plus is more heavily doped, and if you have N plus, that means N is very heavily doped. That's the idea of this plus here, a very heavily doped point. So if you have a P plus N junction, that means Na is much, much greater than Nd. What will W naught be? We can make the simplification then. We had that W naught was equal to 2 epsilon Na plus Nd V naught by E Na Nd to the power half. I'm just rewriting this, and then we'll see how that simplifies down. We've said that Na is much greater than Nd. All right? So basically this term can be ignored. One side is much larger. And then what we have is 2 epsilon Na V naught by E Na Nd to the power half, which then simplifies to, in the case of the heavily doped P plus N junction, W naught is equal to 2 epsilon V naught by E Nd to the power half. Okay? If you're really curious about all the equations, go and look up a book. I'm not going to go through it. We'll never finish anything. I'm still planning to do a little bit about dielectric materials and polymers, so I don't want to take too long on these, since the whole point is not to give you a whole course in semiconductors, but other types of materials too. So this is, we've looked at all the whole p-n junction now in equilibrium, and what I'll do in the next class is to say what would be the current flowing through under forward bias and reverse bias, and obtain a few equations. Again, without going into great detail, we've looked at it a little bit when we considered Schottky. Similar kind of expression will be obtained, and we will go on from there. And then we'll look at maybe some other kinds of devices very briefly. Transistors, a bipolar junction transistor like NPN or PNP. Things that are called MESFETs or MOSFETs are available. JFETs, these are all the abbreviations that are commonly used. Say, for example, JFET is junction field effect transistor. MOSFET is metal oxide semiconductor field effect transistor. And we'll just glance through them, the different kinds of devices that are based on the semiconductor. And then we'll move on to dielectric materials. So that's all for today.